So hello everybody. Today Manish Badarkhe from the Trusted Firmware team will present the topic of migration to PSA Crypto API. Yeah, so Manish, over to you.
Yeah. Hi everybody. Can you guys hear me okay?
Yes, we can hear you.
Okay. Yeah, so as all you are mentioned, I'm Manish Badarkhe. I'm from Trusted Firmware team working over here in ARM. So today we are going to discuss regarding the migration to the PSA Crypto API, which I have implemented recently. Initially we are using some legacy crypto APIs, so we thought better to move to the PSA Crypto API because of its usability and security it is basically giving. So with that, let me just start it with the agenda. So we will in this presentation go through the existing crypto mechanism. That is what exactly the current legacy crypto APIs we are using it in the trusted firmware, and how exactly these are getting leveraged using the embed TLS library. Then we will go through the basic of the what is exactly the PSA, then the design of the PSA Crypto API briefly, and then use of that PSA Crypto API in the TFA for the various purpose. And then what are the various verification using the CI I have achieved using this particular mechanism. And then we'll see what exactly the future scope of using this embed TLS with the PSA crypto driver. Yeah, with that, let me start it with the existing crypto mechanism. So currently this existing crypto module which we have in the trusted firmware is basically leveraging the crypto API function using the software driver present in the embed TLS. So if you see in this diagram, we have the various modules over here like crypto module, authentication module, and image parser module. So all these are taking the part in the authentication process. But today we are mainly concentrating towards the crypto module over here. So we have the one abstraction layer in the TFA, we call it as a crypto module driver. It is basically using various function and then calling the backend registered driver. So in current mechanism of the TFA, we can only use or only register basically only single crypto driver at a time. We don't have the facility currently to register the multiple crypto driver. If you see in this figure right now, this is the default crypto driver, which is basically used by the ARM FPV platform, where we have the built-in software crypto driver, and we have the legacy crypto API basically calling this built-in software crypto driver. This is basically the diagram from the ARM perspective, and this particular crypto driver basically do all the operations such as hash verification, hash calculation, signature verification, and authenticated decryption. So if you go for the another partners which like ST and NXP, which are having their crypto engine currently in the TFA, so this diagram looks like this, where they are not using the software-based embed TLS crypto driver. Instead, they are using their own driver and putting that particular driver inside the TFA. So we have the ST crypto driver today, and we have the NXP crypto driver. Again, we can't use the software crypto and ST crypto or software crypto and NXP crypto at the same time because of the limitation I mentioned is we can only register one crypto driver at a time. So this is what the current mechanism is. And so just look into the challenges and what are the solutions are there. So as I mentioned, like, yeah, the main challenge is we only can register one driver at a time. So dispatching the various crypto operation to the different crypto hardware IPs. So suppose if particular partner may be having different crypto engine and they want to achieve the operations using the hardware capability of that particular crypto engine for the various crypto operations. But currently we don't have that support. Like we can't register two different crypto engines inside our framework. And there are another challenge is we have the two different storage options. One is for the key storage basically. So we currently stored all the keys locally, means during the authentication process. Basically, we extract the key and store that locally and use it. But there is a possibility it may be needed. We don't need it as of now, but in the future we need to extract the key from some secure element, and we really don't want to expose that key in our framework. So yeah, that limitation is there today. And there is no support to use hardware and software crypto support at the same time. Again, I mentioned, yeah, only one crypto can exist at a single time. So there is no way you can achieve some operation using the software crypto driver and some operations using the hardware crypto driver. So all this limitation gets scattered using the PSA Crypto API implementation. So what exactly the PSA? So PSA is a PSA certified is an independent evaluation and certification scheme. It is basically developed by ARM and its security partner. It basically gives one kind of recipe, which is based on the industry best practice. Actually, the scheme is developed by the various partners and they came up with the particular recipe. We'll go through that key aspect of the recipe in the next slide. And they came up with some best practice to achieve this platform security architecture. And also it gives the consistently good security at both hardware and firmware level because again, they actually go through the whole design and then create a specification at every level to find out various security threats and then accordingly create a specification for that. And this basically gives very good guidelines for any platform to go through that particular design as a generic one and then use it. Somebody is novice in that case, they can just follow that guideline and get everything done in the cost-effective way. So what are the 4 key stages of this PSA security? I will not go through too much in details, but just to give you what are the different aspects they are handling it over here. This is basically they are going through the analysis step where they can basically do the threat modeling and developing the security requirement. So different use cases for different security policies requiring different solutions. So they analyze that and create a threat model accordingly. That is again a very much generic threat model. And then according to that security requirement, they come up with the hardware and software specification at architect state. And then we start building the implementation using that particular specification and do the implementation in that style as mentioned in the specification. And then it goes through the independent security testing program to get the certification of the PSA. I'm not going through this analyze, architect, and certify, but what we are currently interested in the implement where PSA Crypto API is basically getting implemented. So there is already a nice specification document already developed. And there is a PSA Crypto API implementation is available from the Embed TLS team and TFA basically using that particular implementation. So just to give the glimpse of like what exactly the PSA Crypto API implementation is. So it mainly consists of two parts. One is a core part. It is basically uh, ensuring the sanity of whatever the argument it is receiving, and then pass them properly to the PSA crypto driver. It builds the argument in a style that is compatible for the PSA driver interface. But this core part does not basically play any role in doing any cryptographic operation. Dispatching this, so the second step, it is dispatching all the arguments to the driver interface, and basically this is what the PSA crypto driver is basically does all the cryptographic operations. So if you look at the how particular template it looks like, so it looks like this, where we have the PSA crypto API, where we are getting all the arguments. We do the sanity checking of that and then build that argument. It is basically in the underlying layer of the PSA crypto API. I mean, we in TFA driver, these are not present. We are just a caller of this function. And then we call this PSA driver interface, and basically PSA driver interface is having such kind of nomenclature. I will go through that in the next slide, what exactly this means. And then it will do all the cleanup operations once the task gets over. So suppose if you want to do the hash calculation, then all the hash parameter get tested over here. Those are passed to this driver. It will do the calculation, and then all the cleanup things happen at this point. So how we are integrating this PSA crypto API into the TFA? So what we have done, we have not basically changed any legacy crypto API implementation, because we are right now grooming into, we are basically validating this PSA crypto API is working in all sense or not. So the legacy crypto API still gets registered as a separate crypto driver, and it is having its built-in software crypto driver. So we have created one new build option to register the PSA crypto API now. And so instead of registering this particular driver, we are registering now PSA crypto driver, which is basically calling all the PSA crypto API inside for the hash calculation and hash verification and authentic signature verification, basically. So during the signature verification, what are the different calls came across? So these are all the calls are there, like PSA set key algorithm. We have to set the algorithm with which we really need to do the verification. So caller has to call this API, give the proper argument over there to set the algorithm. Then what exactly the key type it is, and what are the different uses flag of that, like whether it is for the persistent or where exactly that key gets stored. So all those operations will be done through this one. And then we are calling the PSA import key to get the key ID. I will go through that in details about all these algorithm types and uses flag in next slide. So it will be clear. So PSA import key basically want all these things to be done before, so that all the attributes of the keys get set, and then this implementation receives one key ID, and then that key ID then only get used for the subsequent call in order to do the verification or hash computation or the hash comparison kind of things. So what are the
Manish?
different key attributes?
Sorry, one question on slide 9.
Okay,
Just
9.
earlier, yeah. Here, there is a choice about either using legacy crypto or PSA crypto. Is it a build time choice?
Yes, it is build time choice. Yes.
And essentially, if you choose one, the other is compiled out. Is it?
Yeah, right. Yeah, means other we are not even compiling that file.
And with regards to partners implementation, it's still possible to select? Like you
Yeah,
should
it is
the
still possible to
then
select. So
yeah.
yeah, so it is having all this means at one time any means suppose
Okay.
ST want to do, yeah, they can still use that. They can
Okay.
don't enable this option.
Okay. Thank you.
So coming back to the key attributes, so there are various key attributes surface, and as I mentioned in the previous slide, we want to set the key type. So we want to set the key size, key lifetime, uh, and then the key policies and the key algorithm. So what are these fields basically? So key type is basically we want, suppose with the RSA verification, if you want to do, then I will set this key type as a RSA key, and then its lifetime is divided into basically the two things. One is where this key gets stored and what is its lifetime, whether it is a persistent key or volatile key. So the persistent level gets set along with the location of that key using the lifetime. And we use this policy, like whether it is used for the verifying message or maybe you can use it for the verifying the hash. So you have to set the policy, and then you have to set this hash algorithm, like whether you want to do the SHA-512 or SHA-256 using the RSA, then accordingly that particular algorithm we need to pass it over here. So why basically we are doing all these things is mainly the reason behind it, like we really don't want to expose the whole key. So if you see the current legacy implementation in TFA, we are too much playing around the key by directly exposing to the inside our driver. So the idea here is basically to get the key ID. So the key gets stored somewhere locally, and we then this PSA import key function basically give the key ID, and then that key ID only get used inside our code to just refer that actual key. So the raw data of that key is not really visible for the caller. So the crypto module over here, when you call this import function, it gives all these attributes what I mentioned in the previous slide, along with the key data. So key data is given in the format of DR format, and then it gives the ID which you want to receive it from the PSA Crypto API. So it gives the ID variable which is the output of this API. So once it gets these two things to the import API, the key management layer at the PSA Crypto API store this key and attribute in one of the available slot in the locally and create a key ID out of it. So once this key ID gets generated, then it basically gives back that key ID to the crypto module, and then this key ID will be useful for the further operation. We call it as a transparent driver because we are basically passing the whole key to the import function. But there are cases which we don't encounter in the TFA as of now, where we need an opaque driver, where instead of giving the key, we have to give the location of the key, where exactly it gets stored. And then the secure element basically extract the key and then gives the key ID back to the crypto model. So this whole things we have tested using the various CI test configuration today. We have major boot plus PSA crypto. Basically, it is instead of legacy crypto, I'm using the PSA crypto mechanism in order to do the hash calculation. So if you see over here, the 384 hash 384 is getting calculated, and we are having the FTPM application to just check whether these hashes are getting calculated or not. Another use case is using the trusted boot with the PSA crypto using the RSA algorithm. And same like using the ECDSA algorithm. So we are using the default SHA-256 with this to do the signature verification and hash verification of the various images over here. There are some multiple things also you can do. You can have the RSA root of trust public key, but all the keys which are subsidiary keys which are present inside the certificate, it may be the ECDSA keys. So yeah, that particular combination is also get tested using the PSA crypto. So the changes are out right now. Means few of the changes already got merged. The initial one, which are using the RSA-based crypto verification, those are merged now. And another one is for the ECDSA verification. Those are under review currently because there are some discussions going on. We need to do some calculation for the ECDSA before passing the data to the PSA Crypto API. But hopefully that will get sorted out. And I'm putting some PSA Crypto API references over here. We are using currently the version 3.4.1 embed TLS crypto, and this is where all the embed TLS crypto documentation you can see. So next step is basically to get this whole stack tested on version 3.5.0, which is the latest release from the embed TLS. We have created some helper function in order to convert the DR encoded data to the raw data in case of ECDSA verification. But yeah, those are like temporary helper which are really needed as of now, because we don't 3.4.1 of embed TLS basically needs the raw data instead of DR data in case of ECDSA. But in future, I think they will be coming up some mechanism where we don't really need to do the conversion at the caller side. So PSA Crypto API will do that conversion, and yeah, then automatically everything will work. There is a plan to improve the key management support also. So currently, what we are doing, we are always importing the key and then destroying the key during the each verification rather than saving the key somewhere locally. So at the caller side, we are thinking, yeah, we can basically retain that key ID for some time for the various images verification, because it is possible that different images maybe get signed with the same key. Then we really don't need to always create a different we really don't need to basically locally save that key always. Means we can save it once and then use it for the different purpose, and once the job gets done, then we will destroy it. But currently we have not implemented that way. For every image right now, the key gets imported and then get destroyed. And currently we have not added the support for authenticated decryption. So yeah, soon we will be doing that work once my other patches will get ready and get consumed by the partners. And then yeah, we'll look into it. So this is what the PSA crypto driver API looks like, which I mentioned it over here. So this is the PSA crypto driver API template. So with this one, what we are going to achieve it, as I mentioned in the first slide, we have the challenges like we don't use more than one driver today. But yeah, with this one we can use it more than one driver. But how? So here it is the explanation for that. Like if you see here, the if someone want to use the multiple driver, they can enable this particular define, and then suppose it has a two kind of drivers present, hardware driver, then they can use this X driver and Y driver and enable both the defines. And inside that, they can check the capability of the driver at runtime. If they say like that, yeah, the suppose hash calculation is possible using this one with the specific algorithm, then they will go for this. But if it is not possible, then they will fall through this one and then get it done from the wire driver. And again, if it is suppose if it is not possible by wire driver also, then they can go for the softwarely implemented driver and get the things done. So there are more than one driver they can use it, uh, and that will be really useful for the for various use cases to improve the performance also. Sometimes it is possibly some particular hardware accelerator is slow, sometimes it is another one is faster, then you can do mix and match kind of scenario and get the things achieved in the nicer way. So I'm thinking the future look of the driver will look like uh, there will be no different registration at the TFS side. So what are the different crypto driver we are using, like ST, NXP, and other future hardware crypto driver, all go into the PSA Crypto API layer, like, and they can register their own driver. They can have the multiple drivers also, so that they can achieve like this. And then we will be having one single driver, one same driver, which is doing all possible operations like hash calculation, verification, but all in the generic way rather than having the different drivers. So I'm thinking possibly we will come to this figure in the future once we have all these kind of driver which are present today in TFA get moved to the get moved as a PSA crypto driver. Yeah, with that, this is what I just want to discuss with you guys. If you have guys have any question, just go ahead.
I have one question if nobody dares. I was gonna ask if you're missing any algorithms in the PSA spec at the moment. I was thinking about if you want to implement DICE or something equivalent. Are there any algorithms you found to be missing in the PSA crypto spec?
I'm not really sure about PSA crypto specs, but we are mainly concentrating currently on the RSA and ECDSA kind of signatures verification along with SHA-256 to SHA-512 MD algorithms. But apart from that, yeah, not much doing.
Okay. Well, if you find anything missing in there, the specs I just posted a pointer in the chat are available on GitHub. And if there's anything missing, the right way to do so is create a new issue and indicate that you'd like something to happen, or you wish a new algorithm would be added, possibly with a new API and so on. And that goes on to the roadmap.
Yeah, sure. Yeah, we'll do that one.
I'm not sure if you mentioned Manish, but one part of the rationale for this is also the legacy APIs are being deprecated at some point in the future. We don't quite know when, but from embed TLS.
Yeah, so yeah, I think the move is because of that. Maybe I missed that point. Yeah, so we are going to deprecate, but I think it will take its own time until everyone get moved to this framework. And I think we need to really do it in this way in future. I'm not saying like, yeah, maybe in few of the embed TLS release, if they announce like, yeah, we are not supporting the legacy way, then we don't have choice and we have to move to this kind of framework. Yeah.
Manish, quick question. For the embedded TLS for default PSA APIs, is that something that needs to be selected part of the config, or It's available by default once you compile the embedded TLS itself.
Yeah, so most of the configs are available. Like if you want some RSA and ECDSA kind of verification, yeah, there are few default configs are there that you really need to, but those are really there in the legacy embed TLS config file only. For this
Okay.
particular implementation, there is only one PSA based kind of config we really need to enable,
Okay.
and we found one issue for the for random generation. So PSA crypto init function basically asking for random number to get generated, but uh, we have some workaround in our code today because we are not using any random number generation in the authentication process. So we said like we are using the external hardware for the random number generations, and we are just saying like we are not doing anything over there and just giving like creating some dummy APIs for that.
Okay.
Any other question?
Manish, I don't want if you want to expand on that. Is it worth mentioning the challenge you had with some of the embed TLS API with regards to some difference in the interface when using RSA versus ACDSA?
Yeah, so with RSA, basically the framework currently in the TFA is working in such a way that we are getting the DR encoded kind of public key from the certificate, and then we are passing that to this PSA Crypto API. So when we are using the RSA based algorithm, we are passing this DR format key only, and I think in the PSA Crypto API layer, they are basically properly converting that DR format into the raw format and doing the operations properly. But it is not the case when they are using the ECDSA. The reason behind it, they said like some of the consumers want that ECDSA signature verification API. Means most of the consumers want actually that API should have the raw format input. When you basically when you are using ECDSA format, the API is expecting the raw format data. So caller has to do the action to convert this DR encoded key into the raw format before passing it to that API. So yeah, that is what the deviation today. And for that purpose, we have created some helper function only in case of ECDSA case.
Yeah, sorry, perhaps I missed. Is it at the PSA API interface or embed TLS API interface?
So the temporary APIs are at the TFA level actually, means who are the caller of the PSA Crypto API. Yeah, and yeah, but soon it will go to the PSA Crypto API implementation.
Okay, thank you.
It's worth mentioning also that we've raised this to the Embed TLS team, and that they have plans to provide some variant of these APIs to accept a DR encoded ECDSA key, so that we don't have to do that on TFA side. So we hope that we'll only keep this code in TFA for a short, limited period of time. And when we move on to a future version of embeddTLS, we can just leave that job to embeddTLS library. There's a GitHub ticket open on the embeddTLS project for this.
Okay, thank you. No other question as I gather? Either, so beyond the presentation, is there any general question from the forum towards TFA, topics that we need to follow up on? No. Okay. But thank you then, Manish.
Thank you.
I will stop the recording.